So we saw that a thermal diels-alder type cycloaddition is not going to occur between two ethylene molecules. But interestingly, if we apply UV light instead, we will get a reaction to happen. And normally, if we take a look at the molecular orbitals of ethylene, it's only got 2 pi electrons, therefore there are 2 orbitals. Both electrons would be in the lowest energy, so they have identical HOMO and LUMO. But if we treat ethylene with UV light, we know that molecules, much like atoms, absorb light energy and promote electrons to higher energy orbitals. So what actually happens is we're going to go ahead and take one out and move it to a higher energy orbital. That changes this now to our HOMO, and we have as our LUMO of the other molecule. We no longer have a HOMO or a LUMO in the left molecule. We only have a HOMO. There are no unoccupied orbitals because we've promoted an electron to an excited state. The excited state is higher energy. So we've moved an electron to a higher energy orbital. And now, if we try and arrange these two, we're going to see that, we can get them to overlap nicely. And I'm going to just flip one of them around just so we can see it making sense. But suffice it to say again, one node in each molecule. Normally we can't, of course, react LUMO and LUMO together because there's no electrons there. However, if we promote an electron up to what used to be the LUMO, it is no longer a LUMO, and now we can react it. And so now we see, happy overlap between those two, thereby allowing us to cyclize our molecule. And so by promoting an electron from the HOMO to a new HOMO, which is higher energy, by using UV light, we can get this reaction to be symmetry allowed by promoting an electron to a higher energy orbital. Remember that that's the important part here, is that UV light, H nu as we often write it, when absorbed, promotes an electron to a higher energy orbital. And so we're moving an electron up to a previously unoccupied orbital, which then has the correct symmetry. We now have a new HOMO, so we have a site of electron density with the correct symmetry that can react with the LUMO of another molecule, thereby allowing this to happen. And so, with UV light, we end up getting a cyclization to happen. This is a 2+2 cyclization because we're taking a 2 pi system, 2 electron system, and a 2 electron system, putting them together, getting them to cyclize. And so we see that photochemical reactions can be quite useful for us as well. And in our next videos, we'll see the case of not doing cycloadditions, as we've seen with the diels-alder reactions, but we're going to end up looking at electrocyclic reactions and sigmatropic rearrangements, which will take into consideration that we can either do UV or thermal types of reactions, where with UV we'll end up promoting things to higher orbitals. With thermal reactions, using heat only, we don't change the orbitals. Everything stays HOMO and LUMO as it was. With UV we get a new HOMO, which then may have the correct symmetry that we need. So we'll take a look at these in the context of other pericyclic type reactions when we look at electrocyclics and sigmatropic rearrangements in the next video.